Welcome to our next lesson on solving quadratic equations by graphing. In our last lesson, we talked about quadratic equations and we had a lot of definitions of some new terms. We found out how to find the vertex of a quadratic, how to graph a quadratic equation by using a table. We found out how to find the y-intercept and the axis of symmetry. And so we had a lot of new concepts in our last video. So in this video, we're going to go a little bit further and we're going to talk about actually solving a quadratic equation. And we're going to solve it by graphing. And we're also going to be estimating the roots of a quadratic equation when the roots are not integers on the number line. So we have three kind of terms that we kind of throw around here when we're solving quadratic equations, and those three terms are roots, zeros, and intercepts. Now, we use the term root when we're solving an equation. We say the roots of an equation are this. When we are dealing with functions, we say the zeros of the function are this. And when we're dealing with a graph, we say the x-intercepts of the function are this. All three of these words are referring to the exact same thing. So as you see in your notes, we're going to use those three terms interchangeably. And those roots and zeros and intercepts that we're talking about are where it crosses the x-axis. It's the x-intercept, not the y-intercept. So just a little reminder, a quadratic equation is in standard form when it's written like this, where we have our quadratic term followed by the linear term and the constant after that, and then it's equal to 0. When it's in that form, it is said to be in standard form, and that's the form we want to put all of our equations in before we start graphing or analyzing the equation. So here's an example, and it says solve this quadratic equation by graphing. So when we're solving this equation, we're trying to find values of x that make this equation true. So first of all, we're going to write this as a function in function notation, and then from there we're going to try to find our axis of symmetry. Well, from our last video we learned that to find the axis of symmetry we use the formula negative b over 2a, where b is the coefficient in front of the linear term, a is the coefficient in front of the quadratic term, and in this example b is negative 1 and a is positive 1. So we take the opposite of b divided by 2a, and that gives us an axis of symmetry of positive 1/2. So using that value, we can build a table of values around that value on both sides of that number to get a good picture of what the graph looks like. So I chose some integer values below 1/2 and above 1/2. And the three values I chose below 1/2 are 0, negative 1, and negative 2. And so here are our output values. If you plug those in for x, this is what you get out for f of x or for y. And then for the positive values as well. So now we know from our last lesson that we can plot those points and we get a graph that looks something like this. I didn't use my vertex this time because it was a fraction and it gets a little bit messy, although we're going to have to deal with that anyway. When we have positive 1/2 at our axis of symmetry, I think we ended up with a value of negative 6 1/4, if my memory serves me correctly, for our output value. So from the graph, the zeros are the points where it crosses the x-axis right here, and so they cross exactly on negative 2 and positive 3. You can get that from your table as well, negative 2, 0 and 3, 0, and those two are called the zeros, and they are also referred to as the solutions to the quadratic equation. So that when we're solving a quadratic for x, we're looking for where it crosses the x-axis. Now there are three different types of solutions we're going to run into, three different scenarios. The most common one is where we get two real solutions, which means the quadratic or the parabola crosses the x-axis twice, and each of those numbers or those values where it crosses the x-axis give us a solution to the equation. We might also have a situation where the parabola only crosses once at the vertex. That'll give us one real solution. Or we might have a situation where we don't get any real solutions. And we'll talk about this scenario a few lessons down the road. Okay, so we're not going to focus on that a whole lot just yet, but we'll talk more in depth about that later. So we've been talking about two real solutions. Our last example had two real solutions. Let's take a look at what happens when we have one real solution and no real solutions. So here's an example. I'm telling you up front that it has one real solution. First thing we want to do is put this equation in standard form. So in standard form, we have negative x squared, then we have our linear term, and then we subtract 16 from both sides and get a 0 on the right. So that is the equation in standard form. In function form, same thing, except instead of equals 0, it equals f of x. The axis of symmetry is the opposite of 8, so we'll have negative 8 over 2 times negative 1, which gives us x equal 4. Okay, and so this time I've used my value of 4, my vertex value. And if you plug in 4 here and crank out what you get for y, it turns out to be 0. And then on either side, you get negative 1. And then when you plug in 2 or 6, you get out a negative 4. And I added a third value here of negative 9. So if I go ahead and graph those points, if I plot those points, it opens downward. Remember, if there's a negative in front of your quadratic term, it opens down. You can see I have my vertex here at 4, 0. And so that is the only place that it crosses the x-axis. So there is only one 0, and that 0, or the solution, is x equal 4. Okay? Lastly, we have a situation where we might have no real solution. So here's a quadratic equation, and it's already in standard form. So I'm going to go ahead and build my table of values around the axis of symmetry. There's my function notation. The opposite of b would be negative 2 over 2 times 1. And negative 2 over 2 is negative 1. So the axis of symmetry is at x equals negative 1. So we could draw in that dotted line if we wanted to. If I plug in a negative 1 into my function, I get a value of positive 1 out. I have a negative 1 plus 2, which is a positive, let me make sure I did this right. Negative 1 squared is 1, and 1 minus 2 is negative 1, and negative 1 plus 2 is positive 1. Plugging in a 0, we get out a 2. Plugging in a negative 2, we also get out a 2. 1 and negative 3 give us 5s, and then 2 gives us 10. So these I'm just plugging in the x values in here for x and figuring out what y, or f of x, is for an output. Now I can plot those points, and I've done that for you in the graph. So plotting those points, remember this is a positive quadratic term, so it opens up. Our vertex occurs at x equals negative 1. And so we can see that it never crosses the x-axis. There are no x-intercepts, and when that happens, we say there are no real solutions. So the other scenario we're going to have is sometimes we can't find the exact root by graphing, okay? At least by hand, not without using our calculator. And so one of the things you'll have to do is be able to look at a graph or be able to graph a quadratic equation and find approximately the value of the roots. So again, we're going to use the same process, that axis of symmetry, the opposite of 4, which is negative 4 over 2 times negative 1, which is negative 2, gives us a positive 2. So our axis of symmetry is at x equals 2. And then some values as we build some values around our vertex or around our axis of symmetry. We can plot those points and we have this curve. Now we notice from the graph that it does cross twice. There are two solutions. One of those solutions occurs right here between 0 and 1, and the other one occurs between 3 and 4. So that's another thing you'll have to do in your assignment tomorrow in class, is you'll have to estimate the roots when those roots occur between two integers. Just have to isolate those and tell me what integers that solution lies between. So that should do it for this video, and we will see you in class.